Indeed.
All right.
The broadcast is now starting. All attendees are in listen-only mode.
Hello, I'm Carly Rogers, CAPSA's Marketing and Education Manager. Welcome to the Brass Rod 101 webinar, presented and sponsored by Chase Brass and Copper Company, LLC. We are pleased to welcome two speakers from Chase Brass and Copper, Tom Christie and Larry Muller. Tom Christie is the Vice President of Sales and Marketing for Chase Brass. He's worked for Chase since 1998. And during his tenure, he's held multiple positions, including Marketing Coordinator, Regional Sales Manager, Manager of Marketing and International Sales, and National Sales Manager. Larry began his copper alloy career at Brush Wellman, which is now Materion, working with beryllium copper alloys. After 10 years, he left Brush Wellman to join Chase Brass, where for nearly 24 years he served as Manager of Metallurgy and Technical Services. We're very pleased to have them with us today. Tom and Larry will answer your questions at the conclusion of the presentation. If you think of a question during the presentation, don't want to forget it, go ahead and submit it using your questions tab on the webinar toolbar, but they will actually answer the question for you at the end. 1 hour after the presentation ends, you will receive a webinar survey. It's very quick, very brief. Once you've completed the survey, there will be a link to download today's presentation slides. As well, I'm recording the webinar and it will be available on CAPSA's website and YouTube channel. Hopefully I will have that available for you later today, and I will send an email whenever it is up and ready, and you can feel free to share it with your team and whoever may not have been able to attend today's presentation. So without further ado, I'd now like to turn the presentation over to Tom and Larry.
Well, good morning, everyone, and thank you, Carly. On behalf of myself, Tom Christie, and Larry Muller and Chase Brass, we'd like to just say thank you for this opportunity with CBSA to be able to just share some information about brass rod. So we've put together Brass Rod 101 as kind of a broad presentation that hopefully will be valuable to a new person in the industry that may not be familiar with the material already, and also still have enough content where someone who is very experienced in the brass rod market will still find some value. And so what we're going to do, I'm going to start by turning it over to Larry. He's going to begin the presentation with kind of a metallurgical and process product overview, and then from there, after he covers the manufacturing process and metallurgy, I'll start to focus on the market itself and give an overview of the products and the in-use applications and the current dynamics affecting the market. So again, we appreciate the opportunity to work with CAPS on this, and with that, I'll turn that over to Larry.
Hi, everybody. Since you're a service center organization, this may be the least appealing part of the presentation, but didn't want to get everybody a little bit up to speed on what brass is and the fundamentals, how it's made, and then where, at least from our concerns, are considered where brass is headed. And without making any assumptions on what everybody knows about brass, it's a alloy that starts with copper as the base, and then after that, there's really no hard and fast rules as to what defines a brass. Some people say that it's an alloy with more than 5% zinc. Some people set the minimum zinc content at 15%, but at least in the rod market, the highest volume brass alloy contains at least 35% zinc. And on top of that, then it's got some kind of optional performance-enhancing elements to improve machinability, which is really one of the key factors. And now more and more requirements are to have additions in there that improve corrosion resistance or maybe high temperature resistance. But machinability and corrosion resistance now are the big requirements for rod alloys that are being sold for the potable water industry. There's also residual elements that get into the material because of the types of scrap that are melted to make up our charges, and they can be neutral or harmful to manufacturing. They can cause quality problems. They can cause field performance problems if they are allowed to get out of control, and there's even environmental issues too. It's never a good day here when we see a load of trolley wire come in here, which is a copper cadmium alloy, because cadmium's not a healthy thing if you don't have the right kind of environmental controls in your process to keep them in line. Brass rod is made in a lot of different sizes, at least from 1/4 inch up to 4.5 inches, but you can go in smaller diameters at some mills. You can go to larger diameters, maybe not necessarily always cold drawn, but it's always hot extruded, and then it comes in different lengths. And also for some applications, you may just take the whatever the 10 or 12 inch diameter billets that are cast and turn them in the as cast condition down to a size that gets machined. The biggest volume of brass rod is supplied as rounds, but then it also can be made as hexagons, octagons, squares. The note on there of special industrial shapes, we call them lunch boxes and keyholes and bread loaves and elbows. There's a lot of different profiles that are made to reduce the amount of machining at the machine shop in order for them to make their final product at the lowest cost. For every pound of brass rod that's sold, the industry information is that about 65 to 70% of that is turned away as machining turnings and rod ends, and they all generally get returned to the producing mill because that's good quality input material for our melting operation. And it's an alloy that uses a high level of recycled material. You know, up here on the fourth bullet point, it shows that the charged material is made up of 98% scrap, and then the balance is what's needed to adjust the chemistry to whatever the ASTM specification is, or maybe a special specification on the part of the customer. So turnings, solid scrap, that's the runaround scrap from inside the producing mill gets melted, and then scrap is bought on the free market. And there's about 20 or so alloys that are compatible to the machining alloy, rod alloys that are made now. And that's, in that case, that's where the adjustment needs to be made, because they may just be a copper zinc alloy, and then you've got to add lead, or you've got to add more zinc, or you've got to add copper because the alloy that came in has more zinc in it than what you need in your final mix. And then brass, because of its nature, it can be cast, it can be hot extruded and cold drawn, it can be forged, it can be bent. You know, it depends on the chemistry as to what the capability is of the final alloy and form that the customer needs in order to produce the products that they want to make. Regardless of who makes it, the general process for making brass rod goes through this process flow diagram. You've got raw material receipt and testing, where you separate the wheat from the chaff, almost literally sometimes. You know, it's got to be the right chemistry, the residual elements that we talked about before, iron, tin, nickel, manganese, aluminum, beryllium, tellurium, cadmium, arsenic, antimony. There are limits as to how much of those you can accept based on the product that you're going to cast. And there's also issues with physical shape. Not just because it's brass scrap doesn't mean that it can be efficiently processed through the mill if it comes in what we call a giant bird's nest, which creates handling problems. Or it could be really wet, and that can be an issue in chip melting or melt control in the melting furnace. So we sort all those out, and then whatever passes goes to our melting operation. And once everything is melted, chemistry samples are taken, and from that you determine what you need to correct in one of the elements, if any, so that you are within either ASTM limits, or if you've got tighter internal limits than ASTM allows in order to make your castings. Castings are either direct chill continuous cast, or they might be horizontally continuous cast. and you're making a large diameter billet that's going to get cut and then heated up to make it soft and malleable. And on average, for most of the alloys we're talking about, it's about 1350 Fahrenheit that you have to heat that material to, so that you can get a broad range of sizes extruded out of your extrusion press in preparation for the cold drawing operation. Before you cold draw it, though, you want to pickle it. And that's usually some sort of an acid dip that takes the oxides off of the surface so that it's less abrasive to our tooling for the cold drawing operation, but then also for the machining tooling of our customers, so that they get the longest tool life possible. After it gets pickled, then it gets cold drawn. And cold drawing does a couple of things. First of all, it takes the product down to the size and diameter tolerance that the customer requires for their machining operation. It also increases the mechanical properties and the machinability, so that they can meet whatever requirements that they have for their ultimate customer in terms of strength, or to make the alloy more machinable. The traditional leaded brasses have lead in them that helps with the machinability, but if you don't cold draw it and get that hardness up, as we'll see here in a little bit, you just end up with very gummy material that doesn't break up into small chips and give you the most machining efficiency possible. After that cold drawing or finishing operation, it goes to strapping, where in the bottom right you can see the bundles that are made. In our case, it's 1, 2, 3, or 4,000 pound bundles. In general industry, you could probably get larger or smaller bundles depending on the processing mill. And then it goes on to shipping. Leaded brass has the properties and machinabilities that it does because of the combination of these different elements and then the cold working operation. Copper's got very good corrosion resistance. It's very ductile for cold working, so that different alloys have, as we'll see in the table coming up here in a bit, different alloys have different levels of ductility, so that if you need to bend it or put very coarse threads by rolling into the surface of the brass rod, you've got that available. And then for a few applications, you want good electrical or thermal conductivity. Automotive requirements, for example, might require better electrical conductivity from some alloys than you can get in others, or that you can get from steel, for example. Then you add zinc to make it brass, and that increases the hardness of the copper, for one thing. I'll show you a table here in a minute, but it also makes it even more corrosion resistant. In this case, it makes it more resistant to pitting corrosion. And then you add lead to increase the machinability, and it's kind of a love-hate type of thing when you add lead, because while it decreases the ductility of the material so that you can get the best machinability, it also kind of fights against being able to roll really large threads into the surface of the rod. And consequently, you have alloys that might have less lead and more copper in them to make them more ductile, so you can get more cold formability out of them. Or if you're not concerned about that, then you can get less copper, therefore more zinc and more lead, and that combination gives you the best machinability possible. And then, as we talked about before, cold working increases the hardness, which decreases chip size, but it also can make the alloy a little less cold workable. Going on to the next slide, the old paradigm for machinability was the more lead you put into it, the more machinable it was. Well, because of regulations that have cropped up over the last 10 years or so, and I think Tom talks about that a little bit, you can't solve your machinability issues by just adding more lead anymore. This data here shows that as lead content goes up along the horizontal axis, your machinability goes up, as you can see, along the vertical axis. But without being able to use so much lead anymore, now there have to be different approaches that are taken to get machinability. And you can see the little green triangle to the left is representative of an alloy called 693, which uses silicon in place of lead to make it more machinable. And there's other options too. You can add bismuth, you can add sulfur, we'll talk about in a bit, or you can add combinations of elements to try to get that machinability high so that the cycle times are short for the machinist, but without having any lead in there. The zinc content that we talked about is important for corrosion resistance and making the alloy harder and more machinable. You can see the impact of increasing zinc along the x-axis versus the hardness along the y-axis, or the vertical axis. As zinc content goes up, the hardness goes up, and it reaches a plateau after a while if all you have is a copper-zinc alloy. Once you pass 35% zinc, it really shoots up high. And alloy 360, which is still the dominant leaded machining alloy on the market, is at that 35% zinc level. So you've got a pickup. Actually, it's a little bit above the 35% zinc. So you've got quite a rapid increase in hardness that helps with the machinability. When you add zinc to copper and you cast in these either vertical or horizontal continuous casting operations, your microstructure is pretty coarse. And what you see in the kind of like the light yellow area is what's called alpha phase, and that's 35% zinc, 65% copper, uniform mix. And then you've got this slightly darker stuff in there. It's called beta phase, and that's 45% zinc and 55% copper. And during casting, that just forms naturally. When you heat the brass up for extrusion, it ends up changing the microstructure, so it's all that beta phase. And that's actually a good thing for extrusion because it allows you to extrude a very broad range of sizes from a given input billet size. But you don't want that there after it cools down. And so by proper manufacturing controls, what happens after as the extruded material cools off is that the beta phase goes away. And that's good because beta is very prone to corrosion. What you end up with, if you've done everything right, is that kind of yellowish alpha phase, that's the lower zinc, high copper. And then you can see now the lead particles that were in there to begin with, but were kind of obscured in the casting microstructure. And the lead particles are very fine. There's about 150 million per cubic inch. That's what breaks up the chips during machining so that you get very high machining speeds. And the consequence of the lead distribution and the copper and zinc ratio and the hardness and the cold work is the most machinable alloy of any kind of form, whether it's a leaded steel or a sulfurized steel or aluminum alloys with lead or whatever else they might use in there. Everything is measured against alloy 360 in terms of machinability, where alloy 360 is rated at 100%. And as you get away from using lead and go toward using more or alternative materials or approaches, that's when you have to try to do whatever it takes to get the machinability as high as possible. The effective hardness that you need to get the best machinability can be seen here. When you've got a casting or an as-extruded but not cold-drawn product in front of you, the hardness is about the same, which makes and they're both pretty low, and that's what makes it a gummy machining material, even though you've got lead or bismuth or sulfur or something in there. But cold drawing has a very strong impact on the hardness, so that helps the machinability, but it also works against you in terms of being able to cold work through thread rolling or bending or whatever you need to do to make your final product. So the amount of cold work is carefully controlled to achieve the best balance that you can get in the hardness in terms of the best machinability and the best thread rolling. Now that we're not allowed to use lead galore in our machining alloys because you're trying to make potable water parts, there's 3 different approaches right now that are being taken to get better machinability without lead. One is to have low lead to begin with, and then add something else. And those something else's can be shown in the periodic table. I'm going to show you in a bit. But it's something that's trying to make another phase in there that can break up the turnings. And I have some microstructures that will show you that in a bit. For a number of years, actually for about 20 years, if it's a casting alloy or some of the rod alloys, the rod and cold drawn rods, they use bismuth. And bismuth doesn't mix with brass, just like lead doesn't mix with brass, so there as discrete particles. And sulfur is now getting to be increasingly popular, something that they use that also does not mix with the brass matrix and is there as discrete particles. The other attempt to get a highly machinable alloy is silicon, and either in combination with copper and zinc or in combination with other elements from the periodic table like manganese, for example, can give you in the proper combinations a very machinable alloy, but it's not a soft and smeary like lead combination, and so that can be difficult on tooling unless you do the right type of changes to your tooling and your machining parameters so that it gives you the best machinability. The periodic table has been pretty worked over to try to get different types of brasses that meet different needs. A lot of that is red because you can't add that to copper and have it do anything. You know, the gases on the extreme ends of the periodic table, the radioactive elements, the imaginary ones that down in the bottom right-hand corner of the main chart. You know, none of those are really available, or they make the brass fall apart, like mercury, for example, or they're really expensive. What that leaves you with are the elements that are in green, which are standard alloying elements to brasses. The elements that are in blue are the ones that are added for machinability, and then the ones that are like half green and half blue triangles, those are the ones that work together to make a more machinable material. A lot of the elements that are in there are there for corrosion resistance, for strength, for high temperature resistance. There's some really exotic ones like chrome and niobium that are made as tiny particles and added to copper to make heat shields for the linings of nozzles in rocket engines. There's just a lot of different things that are used for the best mix of elements to get you the properties that you need. For rod alloys in particular, what's really shown up as ones that are well utilized are shown in this table, and you can see alloy 360 is in blue. It's got about 61.5% copper, about 2.75% lead. The balance is zinc, and it's a machinable alloy, and you can do some thread rolling with it. The other fairly popular alloy, in terms of volume for rod is 377, which is the bright yellow roll, and that's got about 58 to 59% copper, 2% lead, and around 39% zinc, and that one's very good for forging, and it's not a bad machining alloy. The cold working alloys you can see in the white rows, 345, 350, and 353, have higher copper contents than 360 typically, lower lead, so the combination of the two give you better ductility, with the main attributes being higher cold workability than 360. So if you've got to bend it or if you've got to thread roll very, very coarse threads for some reason, for pipe threads, for example. Those are the types of alloys they want. The alloys that have come up for the best lead-free, machinability, corrosion-resistant combinations are the ones that are in the either darker yellow, should have been orange, more like orange, or green, the green row. And the darker yellow rows are 27451, you can see 363 and 370, that have different combinations of copper. Some designs of potable water fittings can handle more lead than others, so that's why 363 and 370 are in there. The 27451 and the 363 both have phosphorus, which are in there for corrosion resistance. And then they have the remainder is zinc. The alloy that's in green is 693, and that's got a very high copper, low zinc content because that helps promote corrosion resistance. That has silicon in there that interacts with the copper and the zinc for machinability, and then that also has phosphorus in it for corrosion resistance, plus the zinc is in there for corrosion resistance too. And that alloy can be machine cast or forged, and meets the requirements for corrosion resistance for PEX fittings, as does to some degree the 360 and the 27450, although those are kind of borderline. The difference between these different alloys are microstructurally are shown on the left. And you've got 360 alloy, which is the alpha phase that we talked is the copper and zinc, and then the lead particles that are in there to break up the turnings. The 274-5 alloy that's in the middle doesn't have any lead in it, and it uses microstructure like the grain size and these beta phase particles that are kind of prone to corrosion, but they help break up the chips to some extent. The right-hand microstructure is for the 693 alloy, which is the combination of copper, zinc, silicon, and phosphorus. And that has 3 different phases in it that have different hardnesses, and they help break up the chips during machining. If you want to go with an alloy that contains bismuth or sulfur, it looks a little bit more like the 360 microstructure on the left-hand side. All of these different alloys are being developed to try to meet the changing requirements of the customers who need to make lead-free potable water fittings. They need it to be lead-free or non-leaded because there's a federal lead maximum now for potable water parts. They need the parts to be dezincification resistant and stress corrosion cracking resistant, which are 2 forms of corrosion that copper alloys can experience, and those requirements are dictated by NSF in the NSF 14 voluntary standard for PEX fittings. To reduce costs, there's a certain limited or a certain minimum amount of machinability that these alloys have to meet, or a certain minimum amount of being able to forge it, like alloy 377, or they've got to cast it. And there's the alloy has to be compatible with the sand or permanent mold or die casting process that are currently being used. For parts that are brazed or soldered or plated, you know, the alloy can't have something in there that compromises those capabilities. The alloy should be globally available, and preferably when it comes to scrap segregation, you'd like to mix everything together. But some of these alloys require their own segregated scrap stream to get a minimum of contamination at the mill when they want to take this material and melt it to make new rod. So that's the metallurgy presentation. I'm going to turn it over to Tom for the market overview. Thank you very much.
Thank you, Larry. So shifting gears now, we're going to just kind of give you some insight into brass rod applications, some of the trends that have affected volume in the past to get us where we are today, and then kind of what we see coming at us in the future. So this first page is kind of just a good cross-section, everything from building and construction, transportation, industrial fittings, and coaxial connectors. So the brass rod market, this information is a reference from CDA. They break the end use into certain categories. And so the largest, as you can see, is building and household at 28%. And so that would be everything in your home. That could be a stop valve, that could be a faucet, that could be components in your HVAC system, and that would also be consumer products. So that could be your garden hose or your gas grill or a handheld torch. So that's what would fall into that category. The next one would be component parts, and that is kind of a generic category. There's a lot of companies, as I'm sure most of you know, in the industry that are job shops, and so they make a variety of products for multiple applications, and we as a mill don't typically have really good visibility into where those parts go. So that's kind of a catch-all category that you could apply to many of the other defined segments, but that gives you just a snapshot of the job shop side of things. Industrial machinery and equipment, so those would be your fittings, connectors going into producing mechanical capital for factories, assemblies, that type of thing. Hydraulic, pneumatic fittings are very common in that application. Distributors, which obviously is very relevant to you guys, makes up about 9%, and so the vast majority of distributors are buying, typically not doing a lot of additional fabrication. In many cases, just breaking down to meet smaller order requirements. In some cases, there may be some cutting or packaging. Transportation, that would be primarily heavy truck and trailer. That's where the majority of brass goes. Over the last decade or so, brass rod has lost some ground in automotive, primarily due to weight, as they try to meet CAFE fuel standards, and we'll talk more about that later. Exports, so that would be product outside of North America. That's predominantly Canada and Mexico where that would end up. Electrical electronics, so that's your cable connectors. Again, conductivity related applications, a lot of coaxial things, 50 ohm connectors, and then fasteners and closures is, again, kind of a generic category. So the domestic industry, you can see this is a volume in millions of pounds, has seen a significant reduction. If this actually chart was to go back to 2000, 2001, you would see that total number is up over 1 billion pounds. And so what's really happened to us is a combination of things. You've had, of course, globalization, which really we started to feel the impact of that in 2001 with the recession. A lot of people are facing challenges on their top line, so to protect the bottom line, a lot of things went to lower cost countries for production. So that had, we're estimating, somewhere around a 200 million pound impact on total demand. And then in addition to that, you had substitution, and the legislation, as Larry referenced, has come about, has impacted that substantially. And that's been the drive to reduce and remove lead content. So as products were re-engineered, they were often re-engineered into alternative materials, whether it be aluminums or plastics or composites. In addition to that, you've had just specific applications where parts are miniaturized or re-engineered to be smaller and have less metal. You've had just downsizing. There's fewer domestic producers and consumers here. And then in general, just economic weakness over the last decade. So specific markets, just to give you a snapshot of kind of what's happened. Certainly in building, we talked about it briefly again, but all those plumbing products that had to meet this national legislation actually started in California in 2010, and it set the water pathway as a weighted average of 0.25% lead. That eventually went national here in 2014, and all these producers had to either re-engineer or redesign their products to meet this specification if they were using leaded brass as a part of their pathway. And that's created a proliferation of multiple low lead and lead-free alloys, as Larry referenced, and that's certainly impacted demand, as many of those parts and components were unfortunately engineered into alternative materials. On the consumer front, things like hose couplings are being transitioned to aluminum and steel purely based on cost. In many cases, they're even plating them or coating them to look like brass because that's the preferred material. So that's been purely a transition. You know, copper prices didn't help us when they went up to the $4 range here in the last decade. They have since fallen back, especially very recently. But a lot of those conversions, once they take place, they're hard to reverse. Transportation side, automotive parts are converted to aluminum. We talked about that. That's the fuel standards that are imposed on the corporations producing automobiles. They have to meet these certain targets, and they escalate each year, I think, up to 2025. On the industrial side, fittings are smaller. In some cases, they're using plastic bodies with brass inserts, and that's affected demand. And then on the electrical side, you know, technology is evolving. You know, everybody used to have a cable box and a wire going from their wall to the back of a TV. With wireless and Wi-Fi nowadays, that's less and less common. And the other thing that's happening, quite honestly, is alternative materials, whether it be plastics or composites. There's an enormous amount of R&D and development, so they are being brought to market at a much faster rate than new copper alloys are. From a demand standpoint, this just gives you a feel of what this year looks like. So 300 series rod and bar is classified by CAPSA and is down about 7.9% through October. The CDA, which is the Copper Development Association, our industry data says through November, so this is one additional month, down about 6.5%. So the key drivers, what really impacts demand is a combination of things. First, we always look to the economic indicators, and I've got a slide on that next that we'll go through in detail what those economic indicators are. But they are usually the first visual we use to get a feel for where the market's at and where we think it's going. Legislation, as we said, has had an enormous impact, and we expect that to be ongoing. Right now, it's primarily focused around the plumbing products, but we expect over time that will likely continue and broaden into additional categories. Commodity volatility, a lot of companies, because of the volatility in copper, have chosen to go away from brass products. Again, fortunately, it's worked in our favor recently as copper's dropped, but it's already done a lot of impact to the demand cycle. Overall, housing dynamics are a big deal, and we'll talk more about this. But the demographics of the United States, the number of people being born and immigrating into the country is having a significant effect on that demand. It's also driving household formation. And then the whole concept of single family versus multifamily. And what's happening right now is that multifamilies are growing at a faster rate than single families. And that's happening for a couple reasons. One, the millennials, this next generation, which is estimated between 80 and 100 million people, they're just now starting to graduate, get their first jobs, fill some of the holes created as the baby boomers leave. And many of them are just comfortable renting, or they're not in a financial position to obtain a loan. So multifamilies are growing in numbers and volumes, and that mix affects the housing dynamics as well. Globalization, imported finished goods, still pretty common. There is some ongoing inflation issues, especially in China, that is making some companies reevaluate that, which is a positive thing from a U.S. demand standpoint. But still a lot of stuff going the other direction as well. And then we're seeing an increased focus on machining productivity, yield, product quality, and availability. What U.S. manufacturers recognize is we've got to get better at what we're doing across the board, more efficient, less waste, more lean, more productive, and that's going to have an impact on product requirements and quality as well. So the key economic indicators that we look at is a variety of things. You can see everything from the real GDP to housing starts. If you were to pick one or two, those top two are probably the strongest indicators of what's coming at us. And so you can see 2015 was highlighted there. That's again a forecast because those numbers aren't final. And it was relative to 2010, certainly in the housing side, it's a significant increase. In the case of almost doubling. but at the same time, we haven't seen that phenomenon in brass rod because of the many factors that we've shared with you. But we still think that the growing housing market has additional upside. You can see out to 18 and 19 expected to be over 1.4 million units. And that's, again, a function of the demographics. The new residential, non-residential building, so that's your hospitals, your stadiums, your schools, commercial buildings. All those things, of course, drive demand as well, and that expenditure is expected to continue to increase. Power infrastructure, to a lesser degree, drives some of that. Existing home sales, and the reason that number is important for two reasons. One, as home sales improve, that means demand is improving, and that starts to boost values, which generates demand for new homes. So that is a critical statistic that we evaluate. At the same time, when people buy a new home, they typically are either remodeling it to sell it or remodeling it once they move in. So both of those will often trigger an event that will drive some brass consumption, whether it be a new faucet or a valve or a hose of some kind. Light vehicle, you know, that's been a real strong segment. Again, that's your millennials finally moving out of mom and dad's basement. They're getting their first car, they're getting their first apartment, and we expect that number to continue to remain strong. The fuel standards have, put that pressure on weight reduction, so we've had some impact there. But there's also certain applications that are using more brass components to improve fuel economy within the engine design. So we think there's some positive upside there. The Class 8 truck production, you can see that number is expected to be strong. The biggest bottleneck in that segment, quite honestly, is driver availability. I think in the next 5 years, you're going to see autonomous trucks, self-driving trucks on the road to help fill that gap, because that is an ongoing issue. You know, demand for freight is going to go up, demand for these trucks is going to go up, and we think that'll have a significant impact on brass going forward. Semiconductors is just kind of an indicator of that technical activity in the market, and then obviously a low unemployment rate is positive. So the regulatory requirements, you know, they've had a big effect on our industry and several industries in most cases. And I won't go through each one of these, but you can see there's been multiple series of changes to the lead content. The biggest event was traditionally we had been on a more of a leachate basis, where we're testing the water that goes through these fixtures and fittings. And then in 2010, when California passed the .25, that became more prescriptive, where that's actually defining the materials that can be used in the plumbing product. And so that was a big change. There was a lot of impact to the industry. And going forward, then, of course, when it went national in 2014, had a huge effect across the board. The big one on the table right now is the RoHS. That's up there in 2016. And so there is an exemption for RoHS, which is the European standard for the reduction of hazardous substances. Brass has been exempted and is allowed to retain a 4% lead content. That exemption is set to expire in the middle of this year. Right now, they have requested an extension to that. The many European manufacturers actually have a coalition over there, and they are very confident that extension will be granted, which would give another 4 to 5 years of an exemption. And the reason that's significant is, although it doesn't directly affect the U.S. standards, there's a lot of products that companies do make here that may have brass fittings on them. Those would be affected. So even something like a air compressor that you plug into the wall, this RoHS standard is related to electronic products. That compressor that has a brass fitting on it that happens to be made in Virginia, if it's shipped over to Europe, it would be affected. And so in many cases, if this extension were not granted and they took the lead content down, it would be a 0.1% maximum. And so the only alloy that we make today that would comply with that would be alloy 693, which is the eco brass. The rest of the products we produce and many of the other mills produce, because of the lead content, would not be permissible. So again, we feel that product is going to be exempted for another 4 to 5 years, and we're hoping that decision is made here in the next 30 to 60 days. The ELV, which is referenced down there in 2000, has a similar timeline to it, and we think that that decision will also be made in the same time frame. That ELV stands for end of life vehicle. They're also putting a similar limitation on the lead content. So I think as a distributor, when you call on a customer, if they tell you they need lead-free, what I would suggest you do is you ask more questions, because there's a significant variance in what lead-free really means. So the Safe Water Drinking Act, you know, it was really related to that 0.25%. So in the case of Chase, we make two alloys that are compatible with that, the 2745 and the 693. If it has to be below that, then you need to ask the question, okay, what standard or what specification? So in the NSF 61, that's a more of a leachate type standard, and that's set at 5 parts per billion, which, you know, had traditionally been 15. So that's more of a test where they have to produce a part and submit that sample to NSF for testing to validate if the leachate meets that requirements. Typically, you would have to be below a 360 lead limit to pass that, or have some kind of a post-production wash to remove lead from the surface. The CPSIA, which is the Consumer Product Safety Improvement Act, that actually sets that at a low standard. Right today, there are no domestically produced alloys that meet that lead content. I believe it's 0.03%. 0.01. Down to 0.0. Okay, so it's tiered down to 0.01. And then the RoHS we already spoke about. In general, the EPA, which also has guidelines, theirs is definition of lead-free is 0.1. So again, you would have to be under 0.1 for that to qualify, which again, you know, 693 is the only alloy we produce. There's really very few products on the market today that meet that. So the big picture question is, guys, when you get that question, ask more detail. When you say lead-free, does it mean plumbing compliant lead-free, which is the 0.25? Is it EPA at 0.1? You know, so you can help respond to them with the best information possible. Another factor certainly affecting our market is price volatility. And so this chart here is one we track. Actually, we keep this on our website. So the blue line is Chase's published price. The red line is copper pricing. The green is global copper inventories and the LME and COMEX warehouses. And then the orange line is zinc. So as you can see, quite a bit of volatility really going back to 2002, 2003 when it started, and it's continued ever since. I'd like to say there's a lot of supply and demand logic and fundamentals behind it, but quite honestly, there's not. Back in 2000, the government actually eliminated a law created back in 1936 called the Commodity Positions Act, which limited the position a bank or company could take in a given commodity. And so when they eliminated that in 2000, you can see it took about 3.5 years, and all of a sudden the banks started moving large amounts of money in and out of commodities. And if you were to chart copper or cotton or oil, almost all of them would have a very similar appearance to this. And so the movement of those banks in and out of the commodity funds is really what's creating your volatility. And so unfortunately, I don't see that stopping. Most recently, you're seeing the economic news and the outlook from China in particular has been driving it downward, in addition to a strong dollar. So this is just something we continually track and help educate our customers on. In many cases, our customers will pull what's called a firm agreement with us, where they actually firm up the rod and scrap price so that they can have some stability for a window of time in order to offer that to their customer. The types of metal consumed, again, this is relevant to Larry's presentation, was in the good old days, back, when I started at Chase in 1998, the chips or turnings in the lower right corner represented almost everything we bought. I would say 98, +% was chips or turnings. They were readily available on the free market. We had a large return from our customers, and they were certainly the preferred raw material because they are already to our chemistry, already at a high level of quality. Well, over time, as the industry has evolved and the Asian appetite for copper and copper scrap has grown, the exportation of copper scrap from the U.S. has grown substantially. And so that's actually reduced availability, which has forced the brass rod mills to go up the food chain. And so from a lower right to upper left is the increased cost of these products. So beyond chips or turnings, number 2 would be the next least expensive, then 70/30, then copper chop, number 1, bare bright, and then ultimately cathode. And in some cases we even have to access cathode from time to time just to ensure we have metal requirements. And so that's been a big impact on our industry and the input cost, which ultimately has to be passed on to the consumer. We don't expect this again to change in the near future. We think availability is going to continue to be challenged as global demand for copper and copper alloy scrap continues to grow. So in general, what are the trends we see affecting brass rod? As we already said, we think there's going to be continued pressure to take lead out of products. We think customers will continue to look for opportunities to be more productive and efficient. We've got to continue to take cost out to keep brass parts as competitive as possible. And that's everything from machine at higher speeds to improving yields and reducing scrap generation. There will be increasing demands on quality material performance. A lot of our customers are starting to invest in high-speed machines and bar feeders, and so we've got to have straighter product with better surface to make sure that they can use that to make their parts. We think commodity volatility will continue, as we just discussed. Alternative materials and offshoring will remain threats. We don't see that going anywhere, of course. What we truly believe is the companies that build the strongest supply chains, and obviously you guys are a part of that with your customers, are the ones that will survive. You have to provide a great level of value. You have to be efficient and effective and responsive. And the companies with the best value proposition will be able to survive and protect their customers. Adapting to change is critical to success. If we just made 360 leaded product like we did when I started, we would be struggling to keep the doors open. It's become so critical that we evolve with the market and develop new products to meet the customer demand. And we'll continue to look for opportunities to do that. The good news is, the U.S. is still the world's market. The U.S. demographics are extremely favorable. So the population is expected to grow from about 320 million up to 360 million over the next 15 years. And so just to house that growing population, you need to add about 1.5 million homes per year to ensure they have a place to live. They may be multi-families, they may be apartments. The millennials are much more comfortable living in urban areas and renting. But the end result is you're going to have more demand for plumbing products, for consumer goods, and it should continue to drive the economy forward. So we're still very optimistic about the overall outlook. And that's the conclusion of our presentation. So again, we want to thank CAPSA for this opportunity. Hopefully all of you found some value in this, and you can see our website and contact information is listed there on the slide. If you need to reach us with some questions, feel free to do so. And with that, we'll turn it back over to Carly.
All right, thank you, Tom and Larry. We had a question come in during Larry's portion earlier in the presentation. What is the allowable tolerance for Swiss tolerance specifications?
I would have to look that up. The ASTM dimensional tolerances are broad compared to what Swiss tolerance is. Those are really related more to the old DIN standard, and it only affects the diameter. It doesn't affect straightness, officially anyway. Usually, what people ask for Swiss quality, they're looking for a special high level of straightness. I would have to say, without looking it up, it may be that the diameter tolerance is half of what ASTM allows, given the size and shape.
Okay, sounds good. Well, Tom, I think you already let everyone know that if we have any other questions coming in, someone did ask if the slides will be made available for download, and they will. Here, whenever we end the presentation, about an hour afterward, you will receive a survey. Once you complete the survey, at the end there will be a link to download the slides. So yes, everyone on the call will get a copy of the slides if you complete the survey. And like I said, that'll be available here in about an hour. So Tom, Larry, thank you so much for being with us today. I know that this was a lot of information to take in for everyone. So if you think of anything after the fact, then feel free to reach out to either Tom or Larry with your questions. Visit Chase Brass website and get more information from them. They're definitely there to help you with whatever needs you have. So thank you, Chase Brass and Copper, for sponsoring today's webinar. Tom and Larry for presenting. We really appreciate it. And thank you all for joining us. So until next time, goodbye for today. And like I said, go ahead and complete that survey and we'll get the recording out, and I'll send everyone an email whenever that is available. So probably a little bit later this afternoon, I will have it up there. All right, well, thank you all. Check CAPS's website for upcoming webinar dates and times, and hopefully you'll join us again next time. Tom, Larry, thank you and goodbye.
Thank you.
Bye, everybody.
Bye.